As you all are aware, enzymes are catalysts that increase the rate of a reaction. In this lecture, we are going to look at the parameters that define the rate of an enzyme catalyzed reaction. So, firstly, let's look at the relationship between velocity and concentration for a unimolecular reaction going reactant A forming product P. When we plot the velocity versus reactant concentration, we get a straight line relationship with the slope is equal to K. So the rate equation for such a reaction, velocity is equal to K multiplied by A. This is so when this is called first order kinetics. And the relation the from this relationship you can see velocity is dependent on the concentration of the substrate, so they depend on the concentration of the reactant, right? And as the reactant concentration increases, velocity increases. Now if we do the same thing for an enzyme catalyzed reaction, if we were to plot velocity versus substrate concentration, then we get a relationship which is slightly more complicated than in the case of first order kinetics here, and that is you get a relationship which is the shape of a rectangular hyperbola. So this rectangular hyperbolic relationship tells us quite a bit about an enzyme catalyzed reaction. Firstly, at the early stages of the reaction, as substrate concentration increases, the reaction actually, you see that the rate of the reaction actually increases similar to that of the first order reaction. So at this stage, what you see, the rate of the reaction actually increases just like it does in the case of a first order reaction. And so we say that the enzyme catalyzed reaction follows first order kinetics at initial velocity. Okay. Now, as the substrate concentration increases, this velocity starts plateauing. The velocity starts plateauing, and as substrate concentration increases, the velocity does not continue to increase. So it reaches it reaches a plateau, and so the increasing substrate concentration does not have an impact on velocity. Such a relationship is called zero order kinetics. We say that it follows zero order kinetics at this stage where substrate concentration has increased. Now, the behavior that you see over here is explained by the fact that as the substrate concentration increases, all of the active sites of the enzyme are fully occupied by substrate, and adding more substrate does not increase the rate of the reaction. Adding more substrate does not increase the rate of the reaction, and hence you see a saturation effect. You see, this is called the saturation effect. Now, this relationship can be mathematically described by this equation. VO, which is initial velocity, is equal to Vmax multiplied by substrate concentration divided by Km plus substrate concentration. So Vmax here is the theoretical maximal rate that the reaction can attain. That is when all of the enzyme's active sites are completely occupied by substrate. And Km is a measure of the affinity of the enzyme for its substrate. In order to understand these constants a little better, let's look at how this Michaeli-Menten equation was derived. Now, back in in the early 1900s, Lenore, Michaeli, and Maud Menten proposed a theory which said, where they said that when enzyme and substrate come together, they quickly it forms enzyme substrate complex, and this relationship attains equilibrium rather quickly, defined by these two rate constants, K1 for the formation of the enzyme substrate and K minus 1 for the breakdown of enzyme substrate back to enzyme plus substrate. And furthermore, the enzyme substrate now gradually breaks down at a slightly slower rate into enzyme plus product, and this is defined by these two rate constants, K2 and K minus 2, this relationship. Now, if we were to measure the product formed at the early stages, at initial velocity, then what you will see is that none of the product reverts back to enzyme and substrate, right? It does not revert back to substrate, and therefore we can ignore K minus 2. And so you can rewrite this equation as E plus S, giving you ES, giving you E plus P, defined by these three rate constants, defined by these three rate constants. Now, so you can write the rate of formation of enzyme substrate by this rate equation. Vf is equal to K1 into E multiplied by S, and Vd is equal to K minus 1 plus K2 multiplied by Es will give you the rate of breakdown of the enzyme substrate complex. Now, this theory proposed by Michaeli and Menten was further refined by Briggs and Haldane, who proposed that this enzymes that if you take a closer look at the early stages of an enzyme catalyzed reaction, what you will see is that the enzyme substrate complex, the rate of formation becomes equal to the rate of breakdown, and that the enzyme substrate complex, the concentration of that ES complex does not change over time. That it reaches a plateau, it rapidly reaches a plateau, and it remains the same throughout the catalytic process, and therefore you can say that the concentration of enzyme substrate attains what is known as steady state. So if we assume that, if we make the second assumption, which is the assumption of steady state, then we can say that Vf, the formation of the enzyme substrate complex, is equal, rate of formation of enzyme substrate complex is equal to rate of breakdown of the enzyme substrate complex. And therefore, hence, K1 multiplied by E into S is equal to K minus 1 plus K2 multiplied by ES. And so this relationship can be further resolved. This relationship can be further resolved, and what you get is the concentration of enzyme substrate is equal to enzyme total, concentration of enzyme total multiplied by substrate concentration divided by this ratio of rate constants K minus 1 plus K2 divided by K1 plus substrate concentration. And these rate constants are, this ratio of these rate constants is given the term is defined as Km. Km is a Michaeli constant. So Km is a constant derived from rate constants, and it's called the Michaeli constant. So we can further resolve this equation, and the if we were to look at the rate of formation of product, that breakdown of conversion of enzyme substrate to E plus P, which is defined by K2, is the rate limiting step of the reaction, and therefore we can say that velocity for an enzyme catalyzed reaction is equal to K2 multiplied by ES. K2 multiplied by ES. So, and when all of the enzyme's active sites are completely saturated with substrate at very high substrate concentration, all of this ES is, all of the enzyme is in the form of ES, and so V is equal to K2 multiplied by ET. Okay. So this, when V is equal to K2 multiplied by ET at saturating concentration, then V is equal to V max. So we can say that velocity is equal to V max when V is equal to K2 ET. So in that case, we can actually substitute for ES. I mean, we can substitute over here and we can multiply this. I mean, we can rewrite this equation as velocity is equal to K2 into ET multiplied by substrate concentration divided by Km plus substrate concentration. And since K2 ET is Vmax, we get the equation velocity is equal to Vmax into substrate concentration divided by Km plus substrate concentration. So V is equal, velocity is equal to Vmax into substrate concentration divided by Km plus substrate concentration. This is the Michaeli-Menten equation. So this is the Michaeli-Menten equation. Now, Vmax and Km are both constants. Vmax is that theoretical maximal rate that is never achieved. It is the Vmax is asymptotically approached as substrate is increased, and it would require that all of the enzyme molecules have to be all constantly occupied by substrate for Vmax to be achieved. So Vmax is a constant. Km is also a constant, and Km is a constant that is derived from the rate constant. So what is Km? Km is equal to K minus 1 plus K2 divided by K1. So the rate of formation, K1, is the rate of formation of the enzyme substrate complex. and K minus 1 plus K2 is the rate of breakdown of that enzyme substrate complex. So Km, if the value of if the rate of formation of the enzyme substrate complex is very, very high, if this value of K1 is very high, if it is much higher than the rate of breakdown of the enzyme substrate complex, then this value of Km, is going to be small. Then the value of Km is going to be small. Now, if K minus 1 plus K2 is greater than K1, then the value of Km in that scenario, what's going to happen? Km is going to be large. So you can see that the Km, therefore, is an estimate of that dissociation constant of the substrate from the enzyme, and therefore it defines the affinity of the enzyme for its substrate. It defines the affinity of the substrate for the enzyme. So smaller the Km, higher is the affinity. Higher is the affinity, that means the substrate rapidly diffuses into the approaches the active site of the enzyme and quickly forms the enzyme substrate complex, and it remains bound for longer. That is, that dissociation from the enzyme substrate complex is slower. Now, if on the other hand, if the dissociation is greater, either in the form of breakdown back to enzyme and plus substrate, or by quickly forming product, then both of those factors can influence the value of Km, and Km will be large. So affinity is lower. So higher the Km, lower is the affinity. So you see, it turns out that if you were to plot the velocity versus substrate concentration, when the velocity is half maximal, the substrate concentration needed to reach that half maximal velocity, right? The substrate concentration needed to reach the half maximal velocity, that substrate concentration is Km. Km is the substrate concentration needed to reach half maximal velocity. So if you take another reaction which has, let's say, a graph that looks like this, then what you see is that the substrate concentration needed to reach half maximal velocity. Okay, the substrate concentration needed to reach half maximal velocity is much greater, and so the Km value is higher. So higher the Km, lowers the affinity. So it tells you how much substrate is needed to reach that 50% saturation. How much substrate is needed to reach 50% saturation. Km is defined. So greater the value of Km, lower is the affinity of the enzyme for its substrate. And you can see that this has some physiological significance, because, for example, if you take the enzymes hexokinase and glucokinase, the Km for glucose for hexokinase is in the range of 0.03 to 0.3 millimolar, and glucokinase, depending on the species, is 1.5 to 8 millimolar. So glucokinase has a very high value of Km, hexokinase has a very low value of Km. Both of them catalyze the same reaction, glucose to glucose 6-phosphate. But they're expressed differently. Hexokinase is expressed in most cells, especially in muscle cells, whereas glucokinase is expressed exclusively in the liver and the pancreas. Now, functionally, both of these enzymes respond differently to the substrate. That is, glucokinase responds to a significant spike in blood glucose, like right after a meal. So it only responds to very high concentrations of glucose, and that is what the need of the need is. The liver only enters into uses glucokinase for glycolysis when there's a spike in blood glucose, whereas hexokinase, which is present, has to respond very rapidly to cellular need for ATP, is much more sensitive to substrate concentration, and so it has to trigger the conversion of glucose to glucose 6-phosphate at very low concentrations of glucose, and therefore it has a much lower Km than glucokinase. Now, another parameter we can defined, which we can derive from the Michael-Menten equation by fitting the velocity versus substrate concentration, we can determine this value called K-cat. So if Michael-Menten model fits, if the enzyme follows a simple Michael-Menten kinetics, then when the substrate concentration is saturating, that is, all of the enzyme's active sites are occupied, then the we can say that the K2 is equal to Vmax over enzyme total. K2 is equal to Vmax over enzyme total. And this value of K2 in such an instance is referred to as Kcat, That is the second order rate constant for the conversion of enzyme substrate to enzyme plus product. That second order rate constant can be called Kcat. And Kcat, what Kcat it is that it is the turnover number, that is the number of substrate molecules that are converted to product per enzyme molecule per second when the enzyme is completely, all of the active sites of the enzyme is occupied by substrate. So it defines how much product is made by one enzyme molecule per second, right? And so if you substitute in the Michael-Menten equation, you can plug in Kcat when the enzyme is in the form of when all of the enzyme substrate complex is occupied by substrate, then you get velocity is equal to Kcat. You can substitute. So this reaction. So since I said Kcat is equal to Vmax over Et, Kcat multiplied by Et is equal to Vmax. So what we are doing is we are substituting for Vmax. This is Vmax, and we are substituting for Vmax with Kcat. Kcat multiplied by Et multiplied by substrate concentration divided by K plus substrate concentration is your Michael-Menten equation. Same Michael-Menten equation you substituted with Kcat. So now think of a scenario. So Kcat values range anywhere from 1 per second to many millions. For example, the enzyme catalase converts about 40 million substrate molecules per second. 40 million substrate molecules per second. The carbonic anhydrase converts carbon dioxide to bicarbonate to carbonic acid, about 1 million molecules of carbon dioxide per second, right? So this Kcat can be, so these are enzymes which occur, which have very high Kcat values, but you also have enzymes which have very low Kcat values, like 1 per second. Now, if we consider conditions, where the substrate concentration is really low, then in this equation we can ignore S. And so we can rewrite this equation as V is equal to Kcat over Km, and the enzyme is mostly free. It is not in the form of enzyme substrate complex. So most of the enzyme is in the form of free enzyme, which we can denote as E multiplied by substrate concentration. Now, so you can see this term Kcat over Km, this Kcat over Km can be rewritten in the form of V is equal to K2 divided by K minus 1 plus K2 divided by K1, which is Km, multiplied by E, because we just defined K2 as being equal to Kcat. So that is the second order rate constant. So further resolve this, you can write velocity is equal to K2 multiplied by K1 divided by K minus 1 plus K2 multiplied by enzyme concentration multiplied by substrate concentration, right? So you see this K1 value is the rate of formation of the enzyme substrate complex. And as you can imagine, the rate of an enzyme catalyzed reaction cannot go any faster than the value of K1. That is, we cannot go any faster than the substrate entering the active site of the enzyme and forming that enzyme substrate complex. So it cannot go faster than that. So this K1 limits the rate of the velocity of an enzyme catalyzed reaction. And so if we look at this in this fashion, where we have under low substrate concentrations, the how efficient an enzyme will be is defined by the value of K1. So this Kcat over Km, therefore the Kcat over Km, therefore is called the is also referred to as catalytic efficiency of the enzyme. It defines the catalytic efficiency of the enzyme. So Kcat over Km, the ratio of Kcat over Km defines the catalytic efficiency of the enzyme. And because the value of K1 limits the rate at which this, the maximal limit for this catalytic efficiency. So the limiting factor here is how quickly does the substrate diffuse to the active site of the enzyme. Now, what limits it is the very process of diffusion. So diffusion, that diffusion limit, that rate, the diffusion limited rate, the diffusion limited rate is in the range of about 10 to the power of 7 to 10 to the power of 9, 10 to the power of 9 molar per molar second. Right, so per molar second, that is the diffusion limited rate for a range of substrates. So from really small substrates, really large substrates, that range, the maximal limit, the maximal rate that can be obtained for the diffusion of the substrate to the active site of the enzyme is in the range of 10 to the power 7 to 10 to the power 9 per molar second. This is something that has been determined experimentally. So if this is that upper limit, this is the upper limit that any enzyme can attain, that this is the upper limit any enzyme can attain for Kcat over Km. This is this 10 to the power 7 to 10 to the power 9 molar second is the upper limit for Kcat over Km. This is defined by that diffusion limited rate, and therefore enzymes which actually attain these values in the range of 10 to the power 7 to 10 to the power 9 per molar second, we say are catalytically perfect enzymes. So catalytic, this Kcat over Km therefore is an estimate of how perfect the enzyme is. That is, every time these enzymes, we call them catalytically perfect because every time the substrate diffuses to the active site of the enzyme, it is going to be converted into product. It is going to be converted into product. And so there are several enzymes which actually function at the very upper limit of this diffusion limited rate. And they're, for example, superoxide dismutase, acetylcholine esterase, triose phosphate isomerase. These are enzymes which play very, very significant roles. For example, superoxide dismutase gets rid of the superoxide ions, which are free radicals. Triose phosphate isomerase is a key enzyme in glycolysis and has to respond rapidly to the needs of ATP in the cell. So all of these enzymes function at that very upper limit of the diffusion limited rate. So if you look at this chart here, you can see the Kcat over Km values for some of these enzymes. Acetylcholine esterase is 1.6 in 10 to the power of 8. Triose phosphate isomerase 2.4 in 10 to the power of 8. So these are enzymes which are considered to be catalytically perfect. These are enzymes that are considered to be catalytically perfect. As a matter of fact, superoxide dismutase actually attains comes close. The Kcat over Km comes close to 10 to the power of 9 per molar second. So it is greater than 10 to the power of 9 per molar second. So it is an enzyme which actually defies the limits of diffusion. And the way superoxide dismutase does that is that it actually has charge groups on the surface of the enzyme, which actually pulls the substrate towards the active site. So the Kcat over Km determines catalytic efficiency and tells us how perfect a particular enzyme is. Now, perfection is in terms of the rate is not the only thing that catalytic efficiency determines. It is also a matter of substrate specificity. It's also a matter of substrate specificity. And you might imagine specificity for substrate being something that is defined by Km, but it turns out that substrate specificity is also determined by Kcat. It turns out that substrate specificity is also determined by Kcat. That is for enzymes which are very, very, which have to discriminate between different substrates, like example, proteases and polymerases. It is not just Km that defines the specificity, but rather the Kcat values higher for a particular specific substrate. For example, proteases will cleave after specific amino acids, and even though it may be able to cleave at a different, it can cleave after a different amino acid. How it discriminates is that it has both high lower km values and higher kcat values for the specific substrate. So DNA polymerase is an enzyme where we define it in terms of the fidelity of the enzyme. That is the fidelity DNA. How carefully does the DNA polymerase add the add the nucleotide? That what is the likelihood that it will add the right nucleotide every single time, right? That defines fidelity of a DNA polymerase. A high fidelity DNA polymerase is unlikely to makes very few mistakes. A lower fidelity DNA polymerase might make higher mistakes. So the ratio of kcat over km for the wrong nucleotide over kcat over km for the wrong nucleotide divided by the kcat over km for the right nucleotide. This ratio defines the fidelity. So the lower the value of F, higher is the fidelity of the enzyme, and greater the value of F, lower is the fidelity enzyme. So when kcat over km, when the value is 1, that means there's a 50% chance that it'll add the wrong nucleotide. But as the value becomes smaller and smaller, that enzyme has higher and higher fidelity. So kcat over km is not just simply a matter of the catalytic perfection, but also it can define specificity for the substrate. Now, to make it possible for us to easily derive these parameters of Km and Vmax, we actually can plot the Michaeli-Menten equation as a line equation. That is, we can create as a linear plot. And the way we do that is we can, one of the most popular ones is called the Line-Weaver plot, where you can take take a reciprocal on both sides, begin with the Michaeli-Menten equation, take a reciprocal on both sides to generate this equation. Where 1 over V is equal to Km over V max multiplied by 1 over S plus 1 over V max. And so this fits the equation Vy is equal to Mx plus C, where M is the slope, C is the y-intercept, and Y is the velocity, and X is substrate concentration. X is equal to substrate concentration. So what happens when you so the slope of that of such a fit, this is a typical Line-Weaver fit, and what you see is slope is equal to Km over V max, and the y-intercept is 1 over V max. So we are plotting 1 over V versus 1 over substrate concentration. We are plotting 1 over V versus 1 over substrate concentration, and we get a straight line fit where the slope is Km over V max and the y-intercept is 1 over V max. So what can we do? So here is a simple data set. You have substrate concentration versus velocity, and if I were to simply plot this data, substrate concentration in the x-axis and velocity in the y-axis, then I'm going to get a relationship that looks like this, which is a rectangular hyperbola. Now, if I take the reciprocal of S and reciprocal of V, and I were to plot 1 over V versus 1 over S, then I'm going to get a straight line. And the equation for the straight line, so I can do linear regression. Using Excel, and the equation for that straight line equation, y is equal to 0. In this particular, for this data set, 0.3017x plus 0.0987 will give me the slope and that y-intercept. So I get the slope, this is y-intercept, and y is equal to velocity and x is equal to substrate concentration. So now the slope is equal to Km over V max, and this y-intercept is equal to 1 over V max. So I can now solve for V max. by taking a reciprocal of this number, and so I get 10.131, and I can solve for Km by multiplying 0.3017 multiplied by Vmax 10.131, and I get the value of 3.0567. Now, if the substrate concentration was in molar, then my Km value will have the unit in molar, and if the time is in seconds, then the velocity will be molar second. Right, so the velocity will be per molar second. So the um, um, so that concludes this lecture.